problems where you're testing a lot of cases, or optimization and iterative problems. Needless to say that quantum properties only happen in very small objects at very small scales, such as electrons. So you wouldn't be walking on the street one day and you'll see a cat walking towards you, both dead and alive at the same time. That doesn't happen. All quantum behavior, this superposition and dead or alive behavior, comes down to the fact that all matter behaves like waves. So around 100 years ago, scientists thought that matter, so tangible objects like humans, me and you, tennis balls, a cat, they're different to waves, and it makes sense, right? Waves are what you see on the ocean. Waves are sound waves, light waves. But when people discovered quantum mechanics, they realized that this is not so clear cut. In fact, at the most fundamental level, all matter behaves like waves. And as such, they can be described by what's called a wave function. The wave function is just a mathematical formula, just like a bunch of sines, cos, plus and minus. And it's what you get when you solve the Schrödinger equation for a certain object. You don't have to remember this, by the way, you just have to know it exists. The wave function is not an observable thing. It's a mathematical construct. It contains negatives and complex numbers. So like, for example, when you say hi to your friend on the street, you don't see waves coming out of them, right? That doesn't happen. But what is observable is the probability. The wave function encodes for probability. Let's take, for example, this is a tennis ball bouncing left and right continuously inside a box. The box is closed, so the best we can do as scientists is to model the probability of finding the tennis ball when you eventually open the box. The tennis ball is in a state of superposition. It is in many places at once, a distribution of places. The wave function given by this symbol called psi, when you take the norm and square, so norm, just like in complex numbers, when you norm and square, the negatives and complex numbers disappear, and you're left with this red curve, which is the probability distribution. And so what this means is that it's a bell curve, right? So at the peak of the bell curve, that indicates where it's most likely you'll see the ball when you open the box. However, when the red curve is 0, such as here, that's when it's impossible you'll find the ball when you eventually open the box. And so we sort of liken this to Groot and Drax. When Drax is not looking, Groot is dancing, and when Drax is looking, his quirky behaviors suddenly stop, and it becomes a normal thing. That's exactly what happens in real life. When we open the box, the wave function, we say it collapses due to measurement. The act of observing changes an object, and the quantum properties disappear. So how does this relate to quantum computers? So we said that quantum computers operate in qubits, but what exactly are they? So the most common quantum computer nowadays uses what we call spin qubits. And spin qubits are just, for our intents and purposes, tiny little magnets. And scientifically, we say that magnets have something called a magnetic moment, and that means that they respond to magnetic fields. So let's say you have a handful of tiny little magnets, and you just scatter them on the ground. You have two big magnets, and you put a big south pole here and a big north pole here. Those tiny little magnets will align such that the north poles, indicated in red, will try to point away from the north pole, repelled by it, and they're attracted towards the south. So you end up with something like this. Obviously life is messy, and they'll not be always perfectly pointing to the right. Some will be off-center and skewed, and that's okay. However, in the quantum world, it's completely different. The magnets can either align fully to the right or fully to the left, no exceptions. And so we can rationalize this in terms of states. So in the state that's pointing to the right, we say that's going with the flow, so that's low energy configuration. In the state that's going against the flow, that's a high energy configuration. We can draw energy diagram for this. Additionally, if we label this as state 0, this is state 1, there you have it. These are your zeros and ones, that are your bits. These little magnets are each called your qubits. So in terms of how we manipulate qubits, we have to know the wave function. It turns out that, okay, I've done all the hard work for you. The wave function for qubits takes on this form: A times by state 0 plus B times by state 1. So what do these little brackets, weirdo brackets, mean? It just, in English, it's just a short way to say state. So if it was, you replace 1 with ABC, it would just read state ABC. It just means state, okay? So A and B are complex and can be negative, right? So we can rewrite in this form. But what does this really mean? What does this wave function mean? Well, think not of zeros and ones, but let's say of x and y, right? Let's do some maths. So wave function is A0 plus B1. Think not of this as 0, but x, and think of this as y. What's this? This just indicates a point on the 2D plane. So just like this, x and y. So just as the coefficients a and b would be points on the xy coordinates, a and b for state 0 and state 1 would indicate a possible point in the space which represents all possible qubits. So in maths, you know, we say that this, 1, 0 and 0, 1, these are what? Also normal basis vectors, right? Because they can linearly combine to span the whole 2D plane. So just as 0 and 1 can combine, just as these two can combine to span the whole 2D plane, state 0 and state 1 can linearly combine to span the space of all possible qubits. So what that means is that this formula is actually a general formula. So any qubit can be represented in this form. And the space of all possible qubits is what we call a Hilbert space. Hilbert space is just a fancy name for a generalized concept of the Euclidean space or your Cartesian plane. Additionally, you can simplify this general formula. You can take out this e to the I theta 0. This is what we call a global phase. It turns out it's not observable for a single qubit, so it doesn't really matter. And once you divide through, you end up with this. And this, you end up with new angle here, where it's equal to this angle minus this angle. So this is the most important equation you will learn today. It is defined by the relative coefficients a and b, and it turns out that a and b actually refer to the probability of observing state 0 and state 1 respectively when you open up the box and observe the qubit. And, well, you might ask, why is it under root? Well, remember, the square of the norm, or the wave function, is proportional to the probability. So once you square, it cancels out the root, and the sum of all probabilities must equal to 1. So that's why it's like that. There is also this relative phase theta. This actually defines how one qubit interacts with another. And so to understand what this formula means, we have to explore something called the block sphere, which is an extremely powerful method to visualize qubits. So everyone go to this link. Can someone who's got the link please paste it in the theater chat? Block. Okay. So once you go to that website, actually I'll paste it. Everyone go to theater chat and click on this link. So this is what's called a block sphere. It's a unit sphere, meaning the radius is equal to 1, and that's because the sum of all probabilities is equal to 1. It's a 3D plot, so it means it has an x, y, and a z axis. So let's pay every point on the surface of this block sphere indicates one possible qubit space. So this is all possible qubit qubit state. Right now it's in the 0 position. Now pay attention to what's under the roots. There is a probability of 1 of rolling a 0 when you open the box, and a probability of 0 when of observing a 0 probability of observing 1 when you open the box. This means it's in the 0 state and it's not in superposition. It's like you've looked at the box. So similarly here, this is the qubit in the 1 state because it's impossible you observe it in the 0 state. Okay, now let's do something interesting. Let's sweep down here. So look at these coefficients and how they've changed. So 0 state probability is going down, 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 down until it reaches 50-50. At this point, at this state, the qubit has a 50-50 probability of rolling a 0 state or a 1 state when you open the box. And then when you go down, 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 yep, the probability of observing a 0 vanishes and you're just left with only 1. So what does this mean? It means that as the qubit states go up, down on the z-axis, it changes the relative probability of observing 0 and 1. It doesn't matter where you go, always decreases as you go down. Okay, now let's deal with this xy thing at the equator. What does it mean? So you've learned complex numbers, well, hopefully. We know that we can represent complex numbers on a 2D plane. And this is just basically exactly what that is. There is a special state here called the plus state. And I'll explain why in a second, but I just want you to appreciate the angle, okay? The angle is given by the phase here. So right now it's e to the I0, right? Oops. How do I go back? E to the I0, as you'd expect in a normal complex plane. When you rotate anti-clockwise, see it increases until it reaches pi over 2. And then you increase until it reaches pi. And then increase until it reaches 3 pi on 2 and then back to 0 again. So it's just like your normal complex numbers. So together, this angle, the angle around the equator, along with the relative position along the z-axis, defines it can define any state of any possible qubit. I mentioned that this is called the plus state, right? And the reason why is because e to the I0 is plus 1. And this is the minus state accordingly because e to the I pi is minus 1. So this should make sense. Okay, now we're going to use some maths to prove, to show another form of the plus and minus state. So the plus state is going to be equal to root 0.5, 0 plus root 0.5 e to the I0, state 1, right? So we knew, we said already that that's equal to 1, and root 0.5 is just root half. So this will be 1 on root 2. After you factorize, it looks like this. And accordingly, the minus state will be minus 0.5, 0 plus 0.5 e to the I pi 1. That's going to be equal to half bracket 0 minus 1. So these are important identities, which we will talk about later. Cool. So just as we can write an xy, a coordinate on xy plane as a vector, we can write a qubit state as a vector format, where by convention, the first element is the coefficient of state 0, and the second element is the coefficient of state 1. Here is a new concept called the tensor product. The tensor product is when it's another way of multiplying two matrices or vectors together such that the second matrix is times to each element of the first matrix each time. Yeah, so this will appear same thing 4 times. And the resulting matrix will have dimensions of the first one times the second one. And plain numbers outside will just undergo plain multiplication. It turns out that if you wanted to represent not just one qubit, which is what we've been talking about so far, but multiple qubits, you have to use tensor product on each of the density vectors of each qubit. So let me demonstrate how this is done. So let's say you have qubit 0, which is in state 0. Okay, how do you represent a qubit which is collapsed and in state 0? So by convention, it's this. Q1 collapsed in state 1 would be, by convention, this. See? So these are a sort of cheat way to get to think about this is these coefficients reflect the probability. So it's actually square root of the probability of observing 0. So it's 1. 1 squared is 1, so it's certain, right? Okay, how would you represent two qubits together in a system like this? You would have to do tensor multiplication on Q0 times by Q1. Okay, so this one times by this one times by this whole thing. So it's 0, 1, and then 0, 0. People, please feel free to ping me in the chat if you don't understand. I can go back and do it again. Additionally, you can do matrices. 1, 2, 3, 4. So if you tensor them together, then it would just be, so 1 times 1, 1, 1, 1 will be 1, 1, 1 minus 1. Sorry, that's a 1. And then 2, 2, 2 minus 2, 3, 3, 3 minus 3, 4, 4, 4 minus 4, and so on. So you can do the same with qubits and vectors. Okay, now let's add in a third qubit. So start from 0. Q2 is equal to, let's say it's our plus state. What's our plus state? It's 1 on root 2, 0 plus 1, as we demonstrated before. What does this look like in vector format? It will look like 1 on root 2. Okay, this is 0. Sorry, that. This is a hidden 1 in front, right? So it will just look like this. Okay, what's this with Q2? This will be 0, 1, 0, 0. Tensor with 1, 1 times half. 1 root 2. Okay, so this 1, 1 will go inside this 4 times, right? So it will be 0, 0, 1, 1, 0, 0, and 0, 0. Okay, what's the length of this? 8. So what was the length of the one with just Q0, Q1?
Angel, the slide's blocking the...
Ah! Sorry. Sorry. Yep, that's what it looks like. That's the result. Thank you so much. If that happens again, just, shout out, just like that. Okay. Okay, this was 4, this was 8. So when you have number of qubits is 2, the number of elements in the density vector is 4. When the number of qubits is equal to 3, the number of elements is 8, like here, right? So do we see a pattern? So it's actually 2 to the power of n elements in the density vector that's being generated as you add more qubits. So I want you to realize that, okay, so we just did 3 qubits, 8 elements. If you have 10 qubits, then you'll be here for an afternoon because that's 1,024 elements. So as you can see, this blows up. The good thing about density vector is that it's fundamental. There will always be a vector representation of any state. So if you're going to do this at home, then you just use a density vector as a fallback. Well, I personally do that, and it works every time. Moving right along. Matrix multiplication. I'm not going to review it. We're just going to do it. Cool. So just like classical caveman computers that we use nowadays, quantum computers also use what we call logic gates to achieve the computation, like your AND, OR, XOR, NOT, NAND. Some quantum gates have classical equivalents. For example, this X gate is also called a NOT gate, and it looks like this in a quantum circuit. This is a quantum circuit representation. What it does is an X gate applied to a qubit will swap 0 and 1. If it was 0 before, it will become 1. 1 before, it was 0. Yep, simple. Initialize to... Okay, so let's demonstrate using the block sphere. Where's my block sphere? So initially, qubit is in 0 state. You apply an X gate, and it flips down here. Okay, and then there is something called the controlled X gate. So the normal X gate only operates on 1 qubit, but the controlled X gate operates on 2 qubits. It is such that it only acts as an X gate on a second qubit, so in this case Q1, only if the control qubit, in this case Q0, is in state 1. Yeah, and Papa says you can consider an X gate as a NOT gate from an electrical eng if that's easy for people. Yeah. So you can draw a truth table for the controlled X or C NOT gate. And so, as I said before, when Q0 is 0, then it will be it won't change Q1. So note that the order of these states is Q0, Q1 inside the brackets. When Q0 is 1, then Q1 is swap. 1 becomes 0, 0 becomes 1. And then there's something called the Hadamard Gate, or H gate. What it does is that it places 0 and 1 states in superposition. But what does it really mean? If you Hadamard 0, then it becomes this state. What's this state? We did the math for this, right? This is
Angel, you haven't switched screens.
Ah! Sorry, your ears died. Everyone, I'm sorry. I'm so sorry. Okay, a controlled X gate swaps 0 and 1, but only when the control gate is 1. So this is a control gate, Q0, and this is a target gate, Q1. So you can draw a truth table.
Can't see your cursor.
Do you have to? Do I have to see my... There we go. Ah! Sorry. So we can draw a truth table, mapping the inputs to the outputs. When Q0, so in these brackets, the assumed order is Q0 to Q1. When Q0 is 0, it doesn't do anything to Q1. When Q0 is 1, it swaps Q1. 0 is 1, and 1 becomes 0. There is an additional gate called the Hadamard Gate, which we say it places 0 and 1 states in superposition. Hadamard 0 changes it to... What's this? We've seen this before, right? This is the plus state. When we Hadamard 1 state, it becomes the minus state. Hang on, let me just, it's arc requirements that I need to take a screenshot. So everyone say cheese, even though you can't really say cheese for the camera. Okay. Oh, Conrad's already done it. Thanks, Conrad. Anyways, okay. So let's go back to the block sphere. Oh, I hate this. It keeps on getting rid of my slides. Anyways, everyone can see this, right? Okay. So the H gate. When you start with 0, apply an H, becomes a plus. when you do H gate on a plus, it goes back to a 0 state. Okay, let's say when you apply an H gate to the 1 state, it becomes a minus. Yeah, you apply H gate again, it goes back. So I know you mathematicians are already thinking about something. Yeah, I'll talk about that in a second. But I'll also talk about the Y and Z gates. Well, when you do X gate, it looks like that. You do Y gate, it looks the same, right? But when you do an X gate here, it goes down here. When you do a Y gate, oh, it goes down here. What does that mean? These gates are just reflections of the state vector along the X, Y, or Z axis with a Z gate. So what happens if you do a Z gate to this? It should be here, right? Yeah. So indeed we have it. So we think of gates, quantum gates, as just geometrical transformations. And indeed, that's what they are. Transformations in maths can be written as a matrix. And so, because if we apply, so we've seen that if we apply each gate twice, then it goes back to the original. That means that these matrices are actually the inverses of themselves. And technically these are actually called unitaries because the conjugate transposes its own inverse and has a special property that its eigenvalues always have norm 1. But you don't have to know this. It's not necessary for today. So I'm going to prove to you that I'm actually not lying with this. Okay, so X gate of 0 is, okay, so according to, let me bring that back up. So according to the matrix representation, it's equal to 0, 1, 1, 0 of 1, 0. Okay, so let's do matrix multiplication. So this times by this. So it's 0 times 1 plus 1 times 0, that's 0. Now we do this, and it's 1. Okay, so this does flip 0 and 1, so I'm not lying, right? Okay, let's do a Hadamard Gate on state 0. So Hadamard Gate is 1 on root 2, 1, 1, 1, minus 1. And then this will be, so matrix times a vector is a vector. So this will be 1, and then this times this will be 1. Oh, what's this? 1 on root 2. QED, as the mathematicians say. Yep, so indeed, like when you're thinking about, you can think about gates in so many different ways. Geometrically, if mathematically doesn't work, and mathematically if geometrically doesn't work. So we said that we can represent multiple qubit states in terms of the big 2 to the power of 3 equals 8 sort of density vector, right? And that's coming from the tensor product. So let me illustrate a problem here. So what if you had multiple gates on multiple qubits? And I'm going to show you how you can do a cheat method, or well, not cheat method, fast method. I'll show you multiple ways, so you're not left in the lurch. So let's draw this out again. So this is a quantum circuit, and you're seeing this, I think most of you, for the very first time in your lives. So these quantum circuits, the lines are called wires, and each row is called a register. So there's a register with Q0 and there's a register with Q1. And so what it is that it's a way to represent how the qubits are modified by the gates at each stage. So we can say stage 1 is stage 0 is this, because that's initialized, and then state 1, and then state 2. Okay, so let's do this 2 ways. So we know that. Sorry, I forgot to mention that. Did I mention that? Anyways, just for safety, I'd like to reiterate that qubits are always initialized at state 0. So when you Hadamard a state 0, it will become plus. This is an X gate, so what does it do? It flips 0 and 1, so it becomes 1. So now we can represent the first stage as plus 1. This is perfectly fine. This is what everyone does. And then now you're left with the task of trying to apply only a Hadamard gate to the first qubit, but nothing to the second, but by the 0th qubit. Yes, it's recorded, by the way. Yeah, I'll upload it to YouTube, like all the other workshops. Okay, so let's try to use the density vector to apply our matrix transformation, right? Because this might not be immediately obvious. So this will be a tensor, right? That's equal to 0, 1. This will be 1 on root 2. Oh no, I'm going to run out of space. 0, 1, 0, 1. Okay. Let's try to Hadamard this. What's a Hadamard? Hadamard gate is 1 on root 2, 1, 1, 1, minus 1, right? How are you supposed to multiply a matrix of dimensions 2 by 2 with a vector of length 4? Well, you can't. So are you screwed? No. It turns out that by doing nothing, you've actually applied an identity operator. An identity operator is 1, 1, 0, 0. Yeah. So now what happens is that you have to do, because identity is on Q0 and H is in Q1, you have to tensor them in order before you multiply with this thing. So this will become, let's do a quick tensoring, times, 1 on root 2, 1, 1, 1, minus 1. Okay, big tensor. I'm gonna have to get rid of this. Aha, can't trick me again. 1 on root 2, 1, 1, 1, minus 1. This was 0, 0, 0, 0. This will be also 0, 0, 0, 0, 1, 1, 1, minus 1. And so this will have to be times to this. So matrix multiplied. And that's equal to, okay, so there are two things in front. So this will become root 2 squared is just 2. And okay, let's think about this in a smart way, right? When you matrix times by vector is equal to a vector. You're just going to do this times this plus this times this and so on, right? Sorry, this times this, and the next element is this times this, and the next element is so forth, so forth. We only have 1 here and 1 here, so that means we'll only be keeping these 2 elements and passing them together. So it will be 1, minus 1, 1, minus 1. If you don't believe me, you can...
Angel?
Yeah?
The thing on the left is missing.
Thing on the left is missing. What thing on the left?
You're on your whiteboard still drawing. Yeah, which is... bottom left.
What the hell happens? Okay. Sorry. Why is it missing? How dare you miss? I don't know. Okay, what did I miss? Wait, did everyone see the registers though? Did I draw the registers out, or do I have to start again? I can start again.
I think that's mostly the matrix transformation, the one at the bottom.
Oh gosh, sorry. Okay, so let's do it again.
All the maths was there. It's just like the 2 circles pointing at the bottom left.
Oh right, I don't know what happened there.
Oh,
Did
okay.
I draw this out?
Yeah, yeah.
Yeah.
Okay. Okay, so we've arrived at this point where it's hang on, let me just retrace my steps. Equals to plus tensor with 1. That's equal to 1 on root 2, 1, 1 times by 1, 1. Sorry, 0, 1 equals to 1 on root 2, 0, 1, 0, 1. Okay, and yep, we have a secret identity operator here, so you need to do okay, in hindsight I should not have deleted that, but quick maths.
We got all of that, and then I think it was just multiplying the left-hand side stuff with the.
Yep. Okay, so now we have compatible dimensions 4 by 4 and 4. Okay, so we're going to matrix multiply these together. These together. So do it in an intelligent way. So there are only ones here and here, and this corresponds to multiplications to this column and this column, right? So after you do the matrix multiplication, put it very simply. So 1 on root 2 times 1 on root 2 is just half. And then you'll end up with a vector. So 1 plus 0 is 1. Minus 1 plus 0 is minus 1. 0 plus 1 is 1. And then 0 minus 1 is minus 1. So this will be the result of the second step. That makes sense. So if you don't believe the way I did the matrix multiplication, you can do it at home to verify. You'll get the exact same answer. Let me just move. And I did this weird thing where my keyframe, I started a new page like 10 pages down. Anyways, cool. Let's move along. Yeah, so at home you can do this more complicated circuit, which basically does the same thing, except you have a bigger C0 gate. It takes a long time, but you'll get there eventually. So take-home message is that the register always starts at 0. Use the identity matrix if no operation is to be performed, and the bracket convention is Q0, Q1, Q2, all the way to Qn. So Papa will talk a bit more about how these registers, well, what these registers mean in terms of electrical engineering. Okay, anyone have any questions, or is everyone good? I know it's a lot to take in, so yeah, that's why I'm going to save all my math notes and upload them along with everything else afterwards. Okay, we're almost finished with the math concepts and we're going to move straight on to the algorithm. Last thing that I need you to know is something called phase kickback. So in the quantum world, things are weird. If you try to do something to someone, you might actually end up doing that same action back to yourself. And that's well, it's one of the spooky sort of weirdo properties of quantum. Let me explain. So let's do the math. Go back to the maths presentation. Okay, let's do the left example. So yeah, again, we initialize Q0 at 0, Q0 at state, Q1 at state 0 as well. We have a Hadamard gate and then nothing for one step until we have a C0 gate. That's an H. Sorry, brain fart. H and then plus. Yep. Okay, so yeah, I'm going to show you a quick way to just get around this. Step 0. Okay. State psi 1. This is step 2, and this is step 3. Okay, well, we can actually bypass these steps because we cheat, right? So what's Hadamard of 0 again? It's plus. What's x of 0? It's 1. Oh, what's Hadamard of 1? This will be state minus. Sorry, that's a bit small, isn't it? State minus. And this does nothing, so it remains as a plus. Okay, so by the time you reach number 2, then it will be, by the time you reach number 2, it will be plus, the state will look like this, plus minus. This is Q0, this is Q1, yep. Now it's a C0. Remember what a C0 is? It only flips Q1 when Q0 is equal to 1. So we need to write in density vector format. So this will be 1 on root 2, 1, 1, tensor with 1 on root 2, 1 minus 1. This will be equal to 1 on 2, 1 minus 1, 1 minus 1. Okay, cool. The very, very, very powerful thing about the density vector is that it means something very important. Well, let's put on our training wheels and annotate this. This is actually the coefficient for 0, 0. This is the coefficient for 0, 1, 0, 0, and 1, 1. So how do you rationalize this? Well, remember, these coefficients reflect the root of the probability, right? So when you square it, you get the probability of observing 0, 0, 0, 1, 1, 0, 1, 1. And sure enough, when you square, this half will turn into a quarter. So it will be a quarter plus quarter plus quarter plus quarter. Yeah, and that's consistent with our understanding of probability. Everything adds up to 1. Okay, C0. A C0 gate only flips the Q1 when Q0 is equal to 1. So when Q0 is equal to 0, this is left untouched. But however, Q0 will be 1 in these two combinations or scenarios. What that has the effect on is that this would become a 1 and this should become a 0. Yeah. What does it mean in terms of the density vector? You just swap these. So that means after CX gate, it will be 1 minus 1 minus 1, 1. Okay, now we're going to do the slightly difficult job of breaking this back down, factorizing it back into tensor format. Sorry, untensoring it back into individual qubits. So it will take on the form this.
Remember to remove the slides.
Oh, thank you. I forgot. I keep on forgetting and get too into this. Okay. Yep, so it can be expressed in this form. Okay? This will be Q0. This will be Q1. So it turns out that the only way that this can be achieved is something like this. I'm going to go up like this because I don't have any more room. So what's this? This is, so 1 comma minus 1 is negative state. Negative state. And you can write like this more compactly. So at the end of this computation, you end up with this state. Okay, let's compare to what happened before we did the CX gate. So that was step 2, right? At step 2, Q0 was in plus. Now it's changed to minus. At Q1 was minus, Q1 still minus, so it doesn't change. What have you tried to do? You've tried to use a CX gate. You said that Q0, when you're 1, you should change. You should cause Q1 to flip. But not only has Q1 not flipped, it's been the case that Q0 has itself been flipped. So this is called phase kickback. When you try to do something to someone else, or it ends up doing the same thing to you, and it doesn't affect the person that you were trying to target. So some of you might be wondering, well, okay, this phase kickback is all well and good, right? So you've changed plus to a minus. That's a phase change of pi. So which way? Is it anti-clockwise or is it clockwise? So to answer that question, let's do the second example. So Q0, H, Okay, remember they're initialized at 0 by convention. Okay, let's do the cheap thing again. Hadamard of 0 is going to be plus, x of 0 is going to be 1. Okay, what's this? This is actually a T gate. So this is a controlled T gate. So it basically does similar to what a controlled X gate does, but instead of flipping 1, it adds a phase factor of pi over 4. So let me illustrate. So T is actually 100 ei pi on 4. Sorry, messy. So when you T a plus state, that will be that, and then plus state is 1, 1 times by 1 on root 2. So this will be 1 on root 2, 1 e to the I pi on 4. Okay, so before, in the plus state, theta was 0, right? Now theta is pi on 4. So you've rotated, it just rotates clockwise, anti-clockwise around the Bloch sphere by pi on 4. Okay? So whenever Q0 is equal to 1, then Q1 phase will be rotated, should be rotated anti-clockwise by pi over 4. So do we see that happen? So yep. So yet again, step 1, step 2. Okay. So we need to represent in density vector format. That's equal to 1 on root 2, 1, 1. Density vector by 0, 1. Okay, I have to be very careful when I'm in that area. This will be 0, 1, 0, 1. Okay, draw out our scenario table again. Q0, Q1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so yet again, Q0 is 0 in these two scenarios, so these don't change. Q0 is 1 here, so this T gate will apply to these scenarios. So what it will do is it will times by the phase. So in order to add a phase factor, because this is exponential, right? So you have to times. Times outside means plus inside the exponential. So, and what that means for us is that the density vector will look like this. So 0 times e, 0 times anything is 0. 1 times e will be e to the I pi over 4. This is the density vector. Let's factorize again. So the only way you can get this is in the form of this. So what must these be? So this must be 1, 0, 1. Okay. So therefore, at the second step, this will be how can I represent this better? No, I'll just keep it like that. This is, well, 0, 0, 1 will just be 1. Okay, this is Q1, and this whole thing is Q0. But what was Q0 before? Q0 was plus before, and Q1 was, oh, sorry, down here. Q0 was this before, and Q1 was this before. Q1, yet again, has not changed. 0, 1, and now it's still 0, 1. 0, 1. But what has happened to Q0? Oh, instead of adding the phase to Q1, it's added the phase of pi over 4 to itself instead. So the kickback is in the positive direction. So that means the kickback is anti-clockwise. So it adds to the angle in the complex plane. That's phase kickback. And it's used in a lot of quantum algorithms. So take-home message, at the end of the day, control qubits with the control bit in superposition can cause phase kickback. Okay, any questions? Feel free to chime into the voice chat or type into the theater chat. Ping me because I won't be able to see it properly. Okay. Actually, one more thing that I forgot. If you have a state that's like, let's say you have a state that's like this, right? Q00, Q1 is 0 minus 1. If you do Q0, Q1, right, we said that when you combine two qubits together in a whole system, you can describe using density vector, but you can, if you choose to remain in this bracket notation, then you can still do that. It's just like simple multiplication, like follows. Equals to 0, 0 minus 0, 1. So this is the left-hand side. So we're still mindful of what's on the left and what's on the right. So this will be inserted here and also inserted here. That's how we arrive. And when you want to split it up, we can also factorize just like your normal algebra. So you have to find what's common on the left. So this is common on the left because both have 0. So that's equal to 0. You yoink it out, and all that remains is 0 minus 1. And this will represent Q0, and this will represent Q1 as a whole. Yes? So, well, technically this, technically this is a minor state, just with a global phase. I should be doing this with it to get rid of the global phase, but same principle applies. Oh crap! Wait, I'm sorry, I forgot to flip the page, didn't I?
Yeah, I was about to say.
Can someone tell me when? No. Let's go again. Sorry, we might go over time because of these blunders. Okay, let's go again. Okay, everyone. If you wanted to, okay, I said that if you want to represent these two together, then you can just do you can express them all as density vectors and then tensor multiply. But you can actually tensor multiply as is, just like in your normal algebra. Oh, sorry, big bracket, minus 1. Yep. So what happens is that you can actually put this into here because it's on the left-hand side, and this into here. So that would just become 1 on root 2, 0, 0, minus 0, 1. Done. And when you want to factorize this back, you can do your density vector and factorize that way, or you can you can factorize just like your normal algebra. You take the things that are common to both terms, and then you yoink it out. So 0 is common to both, so you can just literally do 0, 1 on root 2, and then what remains is 0 minus 1. Yep. So this whole thing will represent Q1. This whole thing will represent Q0. And so this is a very quick, cheap alternative to using the density vector, and it saves you a lot of time for certain scenarios. Okay, with that, we'll move on to the algorithm. So the algorithm we'll be learning today is called the Deutsche algorithm. Before we start and explain the problem that it tries to solve, we have to there's a few things we need to clear up. The first term is there is a term called the oracle, and this is a name we give to a function that does a certain job. So you treat it for all intents and purposes like a black box. It's made of some series of gates that someone has made, and it performs this complex algorithm. That's all you need to know. So at this stage, I want everyone to start thinking about qubit states as inputs.
Andrew, you haven't gone back to the PowerPoint.
Yeah. An oracle is a black box function. Just think of it as that way. It's composed of gates, and it's designed to perform some algorithm that someone has done. So at this stage, we need to think about qubit states as inputs and outputs to functions. Functions will modify an input qubit state to give an answer. So here's the problem that the Deutsche algorithm attempts to solve. Let's say that some guy on the street gives you a function f. Now this function f takes n number of arguments, and each argument is either 0 or 1. And with each argument, it either outputs a single 0 or a single 1. So for example, if it's 5 arguments, then one such argument will look like this. And the answer is 0, for example. Mathematically, this is what it looks like. Let's say that the random guy on the street also told you that f must be either constant, meaning all outputs are either 0 or 1. So no matter what you put into this function, it's always going to output 0, or it's always going to output 1. The function can also be, the dude also tells you that it can be balanced, meaning that half of all inputs give you zeros and the other half give you 1. And so we say, well, because each argument, you can either have 0 or 1 for each argument. That means there are 2 to the power of n possible arguments in total. So half of 2 to the power of n is equal to 2 to the power of n minus 1. So n minus 1 arguments will give you 0, and n minus 1, 2 to the power of n minus 1 will give you 1. So here's a diagram to illustrate what it looks like. So this is a function where where n is equal to 1. So it only takes one argument, which can either be 0 or 1. It's constant if when you input 0, it outputs 0. Input 1, it still outputs 0. It's also constant if you input 0 and it outputs 1, or if you input 0 and it still outputs 1. However, it's balanced if one of the outputs is 0 and the other is 1, as shown here. So here's where we learn why classical computers are caveman. So how would you test whether f is balanced or constant on your classical computer, on your laptop? So it turns out the best you can do is to test each case, starting from all the way from f of 0,0,0,0,0,0 all the way to f of 0,0,0,0,1. You can do that, but you can save a bit of time by sort of rationalizing this. You can test at worst case scenario, the most you need to test is only half of all inputs plus 1. So mathematically that means 2 to the power of n minus 1 plus 1. Why? Let me illustrate this. Quick maths. So let's say you have a function that takes n arguments, right? Let's say n is 1,000, and the number of possible combination is equal to like 2 to the power of 1,000, and that's absolutely huge, right? You'll have to test every one of those. Well, half of all of them plus 1. Sorry. So best case scenario is that first try, your answer is 0 when you plug in f of 0,0,0,0. Second try, you plug in f of 0,0,0,0,1, and it gives you 1. Oh, therefore it's balanced because there's no chance it's constant. So therefore you're done. However, worst case scenario is, let's say that it's constant, right? You're given a constant function and you keep on testing. you get 0, 0, 0, 0, 0, 0, 0. Up and until you've tested half of all possible inputs, that's 2 to the power of n minus 1. You have to test one more just to be sure whether it's a 0 or a 1, and then you're sure whether it's truly a constant function or a balanced function. So if the next one that you test is a 0, then you're done. You know it's constant. If the next one you test is a 1, then you know it's balanced. And that can happen with a balanced function. If you were so balanced function means that you have 2 to the power of n minus 1 inputs giving you zeros, and 2 to the power of n minus 1 inputs giving you all ones. If you were so unlucky, well, the probability is very unlikely, but it perfectly well could be that you've just managed to happen to only test all of these for half of the combinations, then, you know, you have, it's a worst case scenario. You have to test one more to observe the 1, and you can conclude it's a balanced function. So, classical computers, you would take ages if n is even like 1,000, which isn't even that much. However, with a quantum computer, you can test it all in one go. So I want you to appreciate sort of the scale of this. So at 35 qubits, we can simulate it on the PC. At 45, you can simulate on a supercomputer. At 60 qubits, it will take you an exabyte of RAM, so that's 1,000 terabytes. And that's more powerful than the biggest supercomputer. And at 100 qubits, a quantum computer that size will be faster than all the supercomputers in the world combined. And at 1,000, practical quantum computers are possible. And at 1,000,000, you might arrive at the meaning of life or something. So the Deutsche algorithm is the algorithm that implements the quantum solution to this testing problem. So what do? You prepare an oracle. So the man gave you that function, right? So you let's say you can model the function using a set of quantum gates, and it will just be something that goes in here called UF. UF will take an input X and add it to a second qubit called Y. And the way this is set up is such that you have set up n qubits. So if you have n arguments to your function, then you have n qubits. And this is called the first register. And the second register would just be 1 qubit. And it's just, it's called an ancilla qubit. And if you know Latin, then ancilla means slave girl. It's just a qubit which is not measured at the end, but it's necessary for the intermediate computations. So what we do is we initialize everything to 0 state as usual. So this 0 superscript tensor n, that just means that we've got n qubits in the same state, which is state 0. These, let's just focus on this first. These will all be subject to n Hadamard gates. So each of these n qubits will be turned from 0 state to plus state. This lone qubit here will be turned by the X gate into from 0 to 1 state. So 1 will feed into Hadamard, which will turn into a negative state. And that's what step 2 looks like. Okay, so let's do some maths to rationalize what's going on here. The next slide. Okay, so at the second step, you have this massive superposition of n qubits plus just single 1 in the minor state. So how do you represent this in density vector format? It will be 1, 1, 1, dot, 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 1. Yeah, because of the way this is. The thing in front will be 1 to the power of 2n. And this will be tensor to the last qubit. How many elements, sanity check, how many elements are in this density vector? 2 to the power of n elements. This is absolutely chungus. This, like, if n is equal to 1,000, then this will be you'll be all day. Well, you spend your whole life drawing that actually. Okay. Let's focus on this state vector. Let's annotate the scenarios. So this will represent each combination of all n qubits. So this will be 0, 0, 0, going all the way to 0, 0, 0, 0, 0, going all the way to 0, 1, 0, 0, 0, going all the way to 1, 0, and so on until you go to 1, 1, 1, 1, 1. It turns out that these will all plug into the oracle independently. So there will be, so it will test 2 to the power of n at the same time. So what the oracle, so if you look in the if you look in the diagram, you have the oracle. First it's y, which means some input, and then it goes y plus f of x. F of x is just the result of the computation for one of these scenarios. Okay, so let's take,
the slide is blocking the.
Yeah, thanks. So let's take this as f of the first. This is the first result. This is the second result, and this is the third result, and so on. F to the x 2 to the power of n. Yeah. And what will happen is that each of these will add onto the ancilla qubit. So the ancilla qubit was initially in the 0 state, right? 0 state is equal to 1. Okay. So when the result is added to the ancilla, we'll call it result plus a and ancilla. It's going to be equal to half of 0 plus f of x minus 1 plus f of x. Okay, and the gate, you can design gates that can do this. This simplifies to, well, 0 plus anything is just that anything, right? 1 plus f of x. Okay, that's great. This will happen 2 to the power of n times. Let's zoom in into this first scenario. What happens if, we'll have to use this tiny space. What happens if this evaluates to 0? Then result plus ancilla will be, that's a jank way of writing it, but you know what it is. Result plus ancilla will be 1 over root 2, 0 state minus 1 state. So it's left unchanged. I'm running out of room. I'm running out of room. Sorry. Yep. But what if f evaluates to 1? Then the result plus ancilla qubit will be, this f of x is 1, so this will be 1 minus, okay, so this that this weirdo symbol just means mod addition in mod 2 because we're dealing with binary numbers, right? So 0 plus 1 will be 1. However, 1 plus 1 is 0. So 1 plus 1, which is the value of the function, is 0. So we go like that. And we can actually simplify, take the negative out. This will be, oh, this appears yet again. So this will be, I'm aware of the space here, equals to negative minus state. What was the result in here? Well, it didn't change the ancilla, so it's just equal to minus state. So can we see a pattern here? So the result added onto the ancilla final state, which is the result plus onto the ancilla, right? It's equal to minus 1 f of x times by the minus state. So this minus state was the state of the ancilla before. And so what we're doing is we're just adding this phase factor of minus 1 or e to the I pi. So why is that useful? We have to think about what it really means in terms of the state vector. So after the computation, these minus 1 to the f of x will actually all be times to each of these elements. And I'll explain why. It's because you tensor producted. Equals to 1 on root 2 to the power of n, 111 times by ancilla, right? So what's the nature of tensor product? It's that the second thing here, in this case the ancilla, goes into the first thing, well, whatever number of times, in this case 2n. So each element will receive this qubit. But you also have the result, which I will draw. Sorry. 1 times minus state, 1 times minus state, and so on. 1 times minus state. So after the computation, when you've passed it through the oracle, UF, you will get this looking thing. Oh, I hate it when my thing goes off the screen. There we go. It will be 1 times the ancilla qubit, which has been unchanged, but it's just modified by this phase f, the result of f of x, and 1 minus 1 to the power of f of x, and so forth, all the way to the end, no exceptions. So what that means is that if we technically didn't need to put the ancilla qubit inside of the tensor, we didn't have to put it inside the state vector, but it was just necessary for me to show you how it works. We can actually, because the ancilla qubit, which is in the minor state right now, it's still in the minor state, it's remained unchanged. All there is the phase factor added to it. We can take out this negative state. So we untensor it, and what you're left with is just, well, 1 times by minus 1 f of x is just minus 1 f of x. Minus 1 f of x1, minus 1 f of x2, dot, 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 minus 1 f of x2 to the power of n. Tensor with the ancilla qubit. So, why is this important? So if balanced, if constant, if the function evaluates to all zeros for all arguments, then this will be rewritten as 1 to the 2 to the power of n. Minus 1 to the power of 0 is 1. Okay, so all 1, 1. If it's all 1, if the function evaluates to all 1, then instead it will be minus 1 to the power of 1. That's just minus 1. So it will just be minus 1, minus 1, minus 1, dot, 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 minus 1. Of course, the ancilla qubit is still lingering around. Okay, the trick is to Hadamard this first register again. What happens when you Hadamard the first register again? These are all ones. This is all in the, which means it's all in the plus state, right? So, Hadamard swaps 0 state to plus state and vice versa. So this will become just 0 state. Everything goes back to 0. And then obviously you have the ancilla qubit, which we can pretty much don't care about at this point in time because we don't measure at the end. What does this mean? It means that when we measure the first these big n this big register of n qubits, we will get all zeros. Is it the same when the function evaluates to all ones? Well, it is pretty much the same thing because when you take out the negative, it's just negative plus n, obviously tensored by the ancilla qubit, but we can just disregard that. So when we Hadamard, sorry about this. So when we Hadamard a minus plus state, well, n of them, well, we can just put this minus out here, right? And so that's equal to minus 0 n. And when we observe, remember, we're taking the norm and the square, and the minus just cancels out. So we get all zeros again. So that means that if it's a constant function, then no matter whether the function outputs all ones or all zeros, when you observe the final array of n qubits, you will always get all zeros because it turns out that way mathematically due to the probability. Now let's consider the case if it was a balanced function. That big, the 2 to the power of n qubits will look like this. Sorry, minus 1 to the power of f of x, minus 1 to the power of f of x, just like before. And this is the 2nth one, this is the second, this is the first. Okay, so let's say that, well, this will evaluate to 1, and this will evaluate to 0, and this will evaluate to 1, right? Then you'll have something, you'll not have a uniform plus 1 or minus 1 in front. You'll have some minus 1, some plus 1, some minus 1, some plus 1. Well, when you Hadamard that, then you'll never, ever get all zeros again. Because well, some of these might be ones, some of these might be zeros, and so you can instantly tell. So take home message. At the end, you reobserve your n qubits, if any of them is equal to 1, then you instantly conclude that it's balanced. If all 0, then you conclude it must be constant. And this all falls out from the maths. So notice how, I want you to go back sort of a little bit and notice how, initially we had the ancilla qubit, right? We had the ancilla qubit tagging along, and it turns out that, well, it remains unchanged. This is another example of phase kickback. It's when your n qubits try to apply a function to turn this initial ancilla qubit into some different result, but instead it's affected itself, and that's what we end up that's why we end up measuring the 0, the 1, 1, 1, 1, 1, 1, and minus, minus, minus 1, minus 1, and stuff. Okay, so I hope everyone got that. I can explain after this while we're doing the hands-on workshop. If you still have any queries or issues about the maths, I'm always free. You can message me whenever. So for those of you interested in the maths, here is just a more rigorous demonstration of how the Deutsche algorithm works, and here is a proof that indeed it's mathematically impossible for you to observe all zeros if you have a balanced coefficient. If you have a balanced function. So with that, it's hands-on time. So everyone go to the Quantum Composer in IBM. So we're going to be using IBM's Qiskit, which is an SDK, and it's just a way to use it's just a way to add gates and stuff using very simple commands in Python. You don't even need to know Python. You just put Lego together. But yeah, it's in the Theta chat. Click on the link. You'll have to create an IBM ID using your email address, and IBM will need you to verify your email address. And
while we do that, do you want me to switch over?
oh yes, please switch over.
Yes. Yeah. I'll